Dates. What an act to follow, right in the middle of siesta time. Bear with me, please. From the corporate down to the grassroots, small family-owned kind of business. I'm a land surveyor. And my passion is to support affordable registration of property rights. So worldwide there are some estimates ranging from 50 to 75% of the world's population living on land of which the property right issues have not been formalized or clarified. So that's basically my background is hardcore land surveying. I know how to use the theodolite, take astronomical observations. I've done the whole thing. I never thought ever that I'd be standing here talking about drones. I don't want to just talk about drones. Just want to talk a little bit about the operational sort of scenario of a small 1 to 2 man company in the mapping business these days. So there are basically 4 phases in each project. The one starts off, of course, with making a client contact. Comes to you via many interesting ways, as we've seen here today. And then you have to get to work. And those are the 2 middle phases. The one is to acquire the imagery and then to build a model out of it. And the last one is to extract information at a scale which is consumable by third parties, by the users. So I'm talking today only about the UAV specific component of a small mapping operation like this. So conventionally, and as a land surveyor, we have to be very careful about accuracy. It was mentioned here before. We're dealing with property rights. So we don't want to, idealistically, we want to bring clarity to property rights. It's a very spatial challenge. We do not want to bring dispute and questionability on boundaries. So we have to be very careful that we don't bring a problem to something that hasn't even been perceived as a problem. So accuracy is very important. And so conventionally, we control our drone models by using ground control to georeference our maps properly so that they fit with legacy data. And spatially, we have harmony with whatever third parties are bringing to the pool of geospatial data available to us in urban design, environmental planning, infrastructure planning, and of course the cadastre, the record of the property rights. So with the advent of structure from motion in about 2011, we finally managed to bring down the mapping aspect with ground control point to the grassroots level. It wasn't quite affordable then yet, but it is becoming so much at a very fast pace. So it's a very automated process that needs to be understood as well. So for the first time, we can make maps without being photogrammetrists because of the high degree of automation. So some ground control points, some aerial imagery, and high presto, there you sit with all of the raster data or the point clouds that you need to extract vectors. And you don't need much in the line of skill in that, except you have to do this ground control work. So there are many people in the world who can do everything mapping-wise, but the georeferencing is always an issue. And legally, because of vested interests in the United States especially, you have to have a land surveyor. If you want to be precise, you can only be precise if you are legally precise. If you're not legally precise, you are illegal. You're a criminal. So, accuracy is being used as a real barrier to a wider community making precise maps. So I've explained why we need to georeference, so I won't go in there, especially because we don't have much time. So what you normally do practically in doing ground control point survey, you have to have some geodetic frame, a reference point on your geodetic reference network, and then you set up a base station there, a reference station, using GPS technology, of course, and then you rove around, you put some targets down the perimeter of the area you're going to map, maybe one in the center, and you rove around with a GPS rover, and that way you get the coordinates. So you have a reference station set up over a point with known coordinates on your spatial reference network. Most of you know this, but many people who operate mapping businesses out of their garages or out of their huts, and I don't mean to be disrespectfully at all, I respect those people very much, they don't have a clue of that aspect. And they have to they're forced to either run to a land surveyor by the law, if they have the capacity to do it, or they just can't do it. So that's the one manual part of putting ground control points down. The other part is in the office. You have to select all the photographs on which ground control points appear, and then you have to observe the image coordinates of the ground control points in those images. So you first of all select the appropriate image. On that image, you identify the aerial target as it is placed down there. Then you have to match that target with the right set of coordinates by moving a marker over the image of the ground control point. And that takes another 1.5 hours, roughly, on a small job, and it takes skills to do that. So, coming back to the overall operational model, you can see here that a considerable effort of the whole mapping object falls into the ground control point provision. Everybody here, I think, who has any experience in georeference mapping will confirm that. You fly for about 20 minutes, but you spend 2 hours in the field because you have to do ground control. So how accurate is this kind of work? We like to be scientific, and we, as land surveyors, are accountable, so we have to do a proper analysis of our accuracy. So we have a test bed, and whatever mapping methodologies we use or procedures we introduce, we test on our test bed by using some 120 checkpoints over and above ground control points, and we use GIS. Thank you very much, GIS suppliers, to do the spatial analysis, and we scale up the errors so that we can visualize the pattern of the errors. So you can see here in this picture that the errors are pointing in random directions, so we are not dealing with a bias here. In other words, this is optimally, the errors are optimally distributed. So at 95% confidence level, we get about 1 to 2 times the pixel size of the GSD accuracy. And this has been a very consistent trend in our business over the last 7 or 8 years. And then, we are always trying to drive the prices down, because the people who are not living on land or who are living on land that is not registered in their name are poor people mostly. So the cost is something that really motivates us. And in about 2011, when RTK-lib came out, which is an open source GNSS processing software suite, I realized immediately that some doors were opening. So we decided to approach drone mapping differently. Instead of georeferencing on the ground, we would fix the camera's exposure positions very accurately with GNSS. So over the years, we tinkered and we bought 3D printers, and we made this little box here. Miniaturizing a survey instrument that's normally this size to this, so that it can be carried on a drone. So that's what we did for ourselves. We are land surveyors. In the meantime, we are now selling it because it does such good service for us. People have contacted us. And so what it involves is a camera that sends a pulse to the GPS receiver every time it exposes. So this instrument here is totally portable from one platform to another. It has nothing to do with flight controller. It just records an event, namely the event of exposure. With that, we get high precision camera positions, which then replace or at least reduce considerably the need for ground control. And here you can see it mounted in a do-it-yourself copter at the top, and a do-it-yourself fixed wing at the bottom, and we produce very good work with those with that arrangement. How it works, the GPS receiver that's mounted on the airplane records a position or records information or satellite information every 0.05 of a second. It runs at 20 hertz. So you get a trajectory that is very dense. Every 15 centimeters or so, if you fly at 5 meters per second, we have a position. A trajectory well defined by closely spaced points. And the camera exposures fall naturally in between two neighboring events or neighboring trajectory points, and we use a timestamp to linearly interpolate the position of the exposure. So you take off the drone. This little receiver, which we call the VMAP receiver, is a blind passenger just hooked up to the camera. And every time the camera takes a shot, the receiver just records the time. And then we post-process the data and we make a table where we allocate the precise position of each image to the image name, and we feed that into the sausage machine, and it gives us the classical geospatial products. So now, looking back again, we can remove from the whole mapping process the provision of ground control points and survey level. So what about accuracy? Somebody asked this question here earlier on. So the accuracy of GPS generally is 1 centimeters in dynamic application, plus 1 part per million of the distance between your reference receiver and the rover. So being metric, it's very nice for me. I can tell you it's 1 millimeter per kilometer, 1 centimeter for 10 kilometers. So it's very precise. But there's a lot of error accumulation and propagation between getting the camera position properly fixed and what is happening on the ground. So that's, again, we don't just believe, we test the technology on our test bed against some 120 checkpoints, and we get exactly the same order of error at 95% confidence level that we get when we use ground control. Not believing these good results, we decided to create yet another completely independent data set by flying north-south instead of east-west, as we did here. And we get, again, same kind of errors. So at some other point in time, you have to convince yourself that this method works. And of course, you can take the average of 2 flights, and you actually discover here, if you pay attention, that a lot of the arrows, the blue and the green, correspond, pointing in the same direction, which actually indicates that the checkpoints might have not been surveyed very accurately. Not accurately enough to actually test this method. Anyway, what does this all mean? How much time? Oh, okay. Am I good already? I'm sorry. So what does this all mean? No loss of precision, significant reduction in manual skills and inputs, savings in time and costs, and for 3D modeling, I have to here in full disclosure tell you, sometimes, unpredictably, we get a bias in the height. It's a constant bias. So over the mapping area, there's no slope there. So if you correct for the height by 1 constant, you still have a very good surface, very good vertical values. The big challenges we are facing all over the world, not just here in the United States, but wherever I go, is the vested interests don't like this at all. It's very, very disruptive, and you have to develop sort of an entrepreneurship that is gentle enough to win the hearts and the minds, not only of those who should benefit from the end product, but also of those who traditionally produce these geospatial products. Because otherwise you just run into battles that you will not win. So, very glad to be part of an activity which lowers the barriers of mapping services, decentralizes mapping capacities. Very nice. You don't need to phone the Department of Mapping every time you want something. Improved community participation because of the high resolution and the fact that every Tom and Dick and Harry can make maps this way. And it basically means it's finally accuracy for all. So we can start demonopolizing precise surveying, making it a grassroots activity at village level. Thank you very much.